Eigenvectors and eigenvalues. So we start with the definition. An eigenvector of an n by n matrix is a non-zero vector x such that ax is equal to lambda x for some scalar lambda. So we have a non-zero vector. Only eigenvector can be a non-zero vector. A non-zero vector. And lambda is nothing else but just some kind of numbers. So the scalar lambda is called the eigenvalue of A, and x is called the eigenvector of A corresponding to lambda. So let's see an example. So we have example, given the matrix and vector u, vector v, check if vector u and v are eigenvectors of A. So to check if a vector is an eigenvector of A, we would need to check if A times u is equal to some number times that vector u. So we're gonna start with the matrix A. We're gonna multiply times vector u. And if we multiply A times u, row times column, we have 3, 6. So we're getting the vector 3 and 6. And from this vector, we can factor the 3 out. If I take out 3, I'm having left 1 and 2. So I rewrote this vector 3 times 1, 2. 1, 2 was my original vector u. So I am able to write this equation matrix times this vector u is equal some number times the same given vector u. So that means that this vector is indeed an eigenvector of the given matrix. Now part B, we would like to check if the other vector Part B is we would like to check if the other vector, that would be the vector u, vector v, we would like to check if that's eigenvector of the matrix. So the same, we're gonna set up if A times vector v, so we're gonna check if A, that's a little bit too big. So what we need to check is A times vector v must be equal to some number, we call that number lambda, times that vector v, if we can find such lambda. So in that case, we take the matrix A, multiply times the vector v, this is my vector v. When I perform the multiplication, I'm getting 3 and 7. 3 and 7, I cannot factor anything out. So there is no number that I could write a number times the vector itself. Therefore, I can conclude that v is not an eigenvector of A. All right, let's look at the next example. So we have example, given the matrix, now determine if the number -1 is an eigenvalue of A. And if it is, then find the corresponding eigenvector. By the definition of eigenvector, we would need to check if A times some vector x is equal to my eigenvalue, which is possible eigenvalue -1, times that vector. That vector needs to be non-zero vector. So if we set up that x has coordinates x1, x2 for some non-zero vector x. So if I add to both sides, I would like to bring this x minus x plus minus x to the other side, I would get ax is equal to 1x is equal to 0. Then we would like to factor the x out. To factor, I would have A plus 1, but I have matrix and I have 1. Matrix cannot be added to the number, so we're using the addition identity, which is the identity matrix. So we have A plus identity matrix times vector x equal to 0. So if this equation has a solution, I mean a non-zero solution, then the number 1 is an eigenvalue of the given matrix. So what we need to do is solve it. So I'm putting my matrix A, this is my matrix A, if you look at matrix A, plus 1, or this would be this identity matrix. So identity matrix has 1 and 1, times my vector x must be equal to 0. So to add it, identity matrix, we would add, notice that we are adding only the main diagonal entries. So 3 plus 1 is 4, and then the 0 plus 0 is 0, 8 plus 0 is 8, and minus 1 plus 1 is equal to 0. So now I need to solve this homogeneous equation, homogeneous because I have 0 on the other side, right? So we can set up we can set up we can set up the augmented matrix of the equation. So I have 4, 8, 0, 0, and 0, 0 from right here, right? So this is my x1, x2, and x3. Perform row operation, divide by 4, I'm gonna get 1, and multiply times you're getting zeros. From this, write the equation. So x1 is equal to 0, and x2 is a free variable, so it's x2. Then we can write this solution for any non-zero number. So I did find a vector x such that my original equation hold. So in that case, I can conclude that -1 is an eigenvalue of A, and the corresponding eigenvector is the vector what we just found it, or any scalar multiple of that vector, because x is any real number. If I multiply times 2, I'm gonna get the same solution to the same equation. In general, we can conclude that if lambda is an eigenvalue of A, then the equation, this equation, A minus lambda identity x equal to 0, has a non-zero solution. Why do we have like this? Because if we start with the AX is equal to lambda x, now if we bring this over, subtract, so we would have that AX minus lambda x is equal to 0 vector. So if I factor the x out, I'm gonna have A minus lambda identity, which is nothing else but what I have right here. So the set of solution, if this equation has a non-zero solution, then we can conclude the equation always gonna have a non-zero solution when lambda is an eigenvalue. If lambda is an eigenvalue. So the non-zero solution, the set of all solutions of the above equation, is called eigenspace. So we know that solving homogeneous equation, we can have 1, 2, or a couple vectors, non-zero vector, so that all the set of vectors, we will call it eigenspace. So here's an example. Is 2 an eigenvalue of A? And if so, find its eigenspace and its basis. So we need to solve A minus lambda identity x is equal to 0. So lambda times identity matrix. So if I have lambda, my lambda is 2. I would have A minus 2. Okay, so we would have A minus, my eigenvalue is 2 times identity matrix. Identity matrix is a 0, 0, 1, 0, 0, 0, 1, 0, and 0, 0, 0, 1, right? So if I multiply this, I'm getting nothing else, but I would have A minus, and on the main diagonal, I'm subtracting 2, 2, and 2. So in the shortcut, what we are doing, we are subtracting negative 2 from the main diagonal right here. That means that you subtract A minus 2 times identity matrix. So if you perform this, then you simplify. What we're getting is this matrix when I simplify that matrix. And performing row operation, we basically need to solve this system. So we would perform row operations and solving. So we're gonna find 1, 0, 1, 0 below. We wanna put 1 in the first spot, make 0 below, and keep going until we get. So what we are getting, if you perform row operation, maybe pause the video and perform the row operations. If you finish the matrix, if you perform all the row operation to the reduced echelon form, we're getting this matrix. And from this, we can see that x1 plus x3 is equal to 0. And in that case, if I move over x3 to the other side, I'm getting x1 is equal to minus x3. Then x2 is a free variable and x3 is a free variable. So then we write the solution to the homogeneous equation, factoring x2 and x3 because they can be any real numbers. And in that case, my eigenvectors are nothing else but 0, 1, 1 and minus 1, 0, 1. So the eigenspace of A corresponding to the eigenvalue 2 is nothing else but linear combination of the vectors that we just solved. Since the vectors are linearly independent, they form a basis for the eigenspace. So the basis would be just those two vectors. Okay, so now we have example. Let A be an n by n matrix, and if X is an eigenvector corresponding to lambda, then any scalar multiple is also an eigenvector corresponding to lambda. We already saw this from the example. Now we would like to maybe prove it or show it. So what is given? Given is my matrix A, n by n matrix, and X is an eigenvector. What does it corresponding to the eigenvalue lambda? What does it mean that X is an eigenvector? By the definition, that means that A times vector X is equal to lambda times X. So what we need to show is that Kx, and a scalar multiple, is also an eigenvector. So what does that mean? That A times Kx must be equal to lambda times Kx. So we start from the left side of that equation, A times Kx. By the properties of vector matrix multiplication, the K can go in front. So we're gonna have K times AX. Now for this part, we will use the given AX is equal to lambda X. So we substitute lambda X. So I have K times lambda X, and then the lambda is a number, so can go in front. So what we did, we started with A times Kx, and we show it that it's equal to lambda Kx. So that means we show it that the Kx is indeed an eigenvector for any non-zero number k. It should have been added for any non-zero number k. All right. The eigenvalues of a triangular matrix are the entries on the main diagonal. So if you have, the proof is a little bit more complicated, so we will just justify that you can see how that works. So if I take any triangular matrix was the matrix that has kind of formed the upper triangle. In that case, it's called upper triangular matrix, right? I'm sorry, I just erased it. Okay, so if I have the matrix, let's say that my main entries are 1, 4, and 6. So I would like to, so the eigenvalues are 1, 4, and 6. That's what the statement says. So let's check it for 6, for example. So for lambda equal to 6, we would need to solve the equation A minus, this would be 6 times identity. 6 times identity matrix X, we would need to find a non-zero vector X. So if I subtract 6 from the main diagonal, because identity has only main diagonal entries, so look at the original matrix, and we would like to subtract from the original matrix. So we would subtract we would subtract minus 6 on the main diagonal entries. So I'm going to have 1 minus 6 and so on. And if I calculate this correctly, then that's what I'm getting. So notice that I have always going to have a free variable because one of the main diagonal entries will disappear. I'm going to have a 0 row. In that case, this is going to be my pivot position, and this is going to be my second pivot position. And I still have a free variable. This would be my x1. This would be my x2, and this would be my x3, and this would be a number. So I can see that I do have a pivot position. So since we have a free variable, this equation will always have a non-zero solution. So therefore, indeed, the main diagonal entries will be eigenvalues of that matrix. Now let's see next example. So if A is an invertible matrix and lambda is an eigenvalue of A, we would like to show that 1 over lambda is an eigenvalue of A inverse. So given this matrix is invertible, what does that mean, that matrix is invertible? That means that A times A inverse is identity, and or A inverse times A is also identity. And let the lambda be an eigenvalue of A. What does that mean? That A times X is equal to lambda X for a non-zero vector X. What we need to show that 1 over X is an eigenvalue of the inverse. So that means that inverse times some other vector, we call that vector Y, is equal to my eigenvalue, which is 1 over X, times that non-zero vector Y, for some non-zero vector Y. So the proof, we're gonna start with the given. So this is the given equation. Ax is equal to equal to lambda x. We would multiply both sides by the negative a inverse on both sides. And by definition, A inverse times A is identity. Identity times X is just X. And on this side, I can move lambda is a number, so the number can go to front. So lambda is in front. And then if I divide both sides by lambda, I'm getting 1 over x. This would cancel out. And on this side, I would get A inverse times times x. So what we have is A inverse times x is equal to 1 over lambda times x. So what that means that my vector y is nothing else but x, and this proves that 1 over x is an eigenvalue of A inverse. Next example, we have lambda is an eigenvalue of A if and only if lambda is an eigenvalue of A transpose. So eigenvalues of the matrix are the same as eigenvalues of A transpose. So a given matrix and transpose have the same eigenvalues. So if I have a given eigenvalue, that means AX is equal to lambda x for a non-zero vector x. Then if I take transpose on both sides, what happens if we remember that A, B transpose is nothing else but B transpose times A transpose. We change the order by the definition of transposition, right? So that's exactly what I'm doing here. A is a matrix, X is a vector, but vector is a special case of the matrix. So we would have that X transpose times A transpose is equal to lambda times X transpose. We could have changed the order here, but lambda transpose of a number is just number itself. So that's why the lambda stays as is. And what that means, that the lambda is an eigenvalue of X. The lambda is an eigenvalue of the matrix A. Now we have theorem if V1, V2 are eigenvectors of the that corresponds to distinct eigenvalues of A, then the set is linearly independent. So if we have distinct eigenvalues, then the set is always linearly independent. The set of eigenvectors that correspond to different eigenvalues. Okay, so now we have example. Now we have example that the given for the given matrix A, for the given eigenvalue, find the corresponding eigenvector. Are the vectors linearly independent? So we have a triangular matrix. We know that the eigenvalues are the numbers on the main diagonals. So the eigenvalues of the matrix are 1, 2, and 3. So to find eigenvectors, we need to solve the equation AX. So let's find eigenvectors corresponding to lambda equal 1. We solve the equation AX is equal to 1 times X, bring this over. In other words, we're solving this equation for a non-zero vector X. So minus identity, perform this. If you perform this, you're gonna get this matrix. This is the augmented matrix, and this is the zero row. So we have this X1 first column, X2, X3, and the numbers, of course, right? The last one is the numbers. So if we simplify, we're getting this matrix, then we need to reduce to the matrix, use row operation to reduce to reduced echelon form. So if I switch, I would like to have 1 in the first position. So if I switch this using this one, then if I switch the rows, I'm gonna get this matrix and keep performing row operations. So -3 gets 0, keep performing now. So I have pivot in the first position and this one. So I have 1, 0 below. Now I need to get 1 and 0 above. So I need to make 0 above. So keep performing the row operations. We can switch row 2 with row 3. And to get this 1, and then we can add it 13. So the reduced echelon form turns out to be this way. So solve the system. X1 is, I don't have X1 here, so X1 is a free variable. x2 is 0, x3 is 0. So we have x1, x2, x3, factor the free variable, and this is the vector. So the eigenvector corresponding to the given eigenvalue is equal to 1, 0, 0. That's my vector taken right from here. And now we repeat this whole process. This whole process we would repeat for the other eigenvalues, for the eigenvalue 2 and for the eigenvalue 3. So for the eigenvalue 2, we have to solve this equation for a non-zero vector x. So that means we're subtracting 2 on the main diagonal. That's basically what it says. We're subtracting 2 on the main diagonal from the original matrix, and this one is the 0 column. So perform the row operations, reduce, basically solve the system. If you solve the system correctly, you should get the solution. So the eigenvector corresponding to 2 is this eigenvector. And we would repeat the process for lambda equal to 3. So we would solve the system a minus 3 identity x equal to 0. So what we are doing, we're subtracting 3 from the main diagonal. That's how the 3 times identity, because identity has only numbers on the main diagonal. So perform row operations to solve the system, and we're getting the eigenvector as well. So for lambda equal 3, the eigenvector is -1. I'm sorry, the eigenvector is this vector. So now if you want to check linear independence, you can check and convince yourself that indeed those vectors are linearly independent.